All right, we are recording. So just wanted to welcome all to our Wednesday class for lenses. This is probably gonna be the last one we do of these because next week your paper is due, and that is going to lead into the final, and then that's it, and you're free for the summer. Hopefully, it's not too much stress or work for you to get the paper done. But for lenses, and I really like doing this lesson because it really teaches you a bunch of people about how your eye works. Yeah, I know, summer in quotes. I get it. But you at least don't have to take the attendance roll every morning. There's that. But as for the question I have up on the screen, which is what color is this called? And most people are like, oh, it's red or it's brownish red. Oop, that's people coming in. All right. And that is true. It's what we can call that. But can you prove to me that that is the same color that I see? Can you convince me that that red is the exact same shade of red or even the color red that you see? Like, think about it. How would you describe it? If I held up something red in front of the screen like this, and I said, prove to me that that is the same red you see, how could you even describe a color to somebody? This is actually a thing that a lot of people, it's kind of like saying, hey, describe sight to a blind person. And it's like, well, if they've never seen before, how do you describe a color or something like that to a person that's never seen that? And the thing is with color, it's a very personal experience because it is the version that your eyes interpret and the chemical signal that gets sent to your brain and the way your brain interprets it. So technically, for all we know, the color red that has a certain way of looking to us could look very different to somebody else. And because from the day they were born, they went, oh, look, red. And for them, it could look something, like green or blue or purple. And they were told that's red. So, like for all their life, someone could have put up in front of them something like this kind of box. And they were told red. This is red. And they went red. And for all their life, that's all they were told. Because how do you prove that the red I see is the same red you see? We can't. In fact, there's a group of people who don't even see red very well. I'm going to try and get into that. Yeah, we're going to go into color blindness a little bit. I'm going to make sure my text keeps updating. Oop. Doesn't the color appear like that based off of how light is reflected in the eyes? It's how it's the vision on the sharpness is how it's refracted, but the color blindness is actually based on a chemical in the back of the eye. Now, we're going to actually show you a person who actually has color blindness, and you can kind of see the versions he sees the world in. So, like I said, I'm going to try and play this for a few seconds, and we'll see if the audio syncs up. I don't know if it does on this, but this is a guy. He has color blindness, and so he's going to take some color blind tests. Now, there's no closed captioning for this episode. Wonderful. Okay, just out of curiosity to anyone in the stream, could you hear that? Like, could you hear the audio from there? Dang it. Okay, well, then let me just kind of go back and forth on what he's doing. So the one on the left side is what's recording, and the one on the right side is the approximation of what his eyes actually see. Now, he has a version of red-green color blindness. That means he doesn't actually have a properly formed pigment in the back of his eye, a properly formed chemical structure in his eye that reacts to red the correct way. Either it's missing or damaged or there's not enough of it. It depends on the version he has. If he can't do that, it's called red-green color blindness, and it's the most common type of color blindness. Red actually just looks like a darker green to somebody who actually has all three pigments. So I'm going to play just a few of these so you can kind of see. He says like it's 5, that's easy. He can tell it's a 9. 7, he's able to tell right away. Eight, he can tell. Now you might notice right here, you can see this one is quite a bit faded compared to the one over here. And it's because it's closer. These reds are closer to the green spectrum on him that are close to darker colors. So it's harder for him to see. Yeah, you can see the red ones are much more harder for him to see. And he's like completely, he's like, it's faded. He's like, I can see some lines. And eventually, like here, he can't quite see the three at all. And in fact, he even starts saying eventually that it starts fading in and out, that it's really difficult for him to see. But imagine that's the difference in the vision between these two, between someone who has color blindness and not color blindness, is that me or most people would see a three, even if it's a little faded, they still see it. On the right, it's gone. It's not there. That's why this test is there for. It makes it so that the little dots are closer to a certain color than others, making it harder to see. He can sort of tell. He kind of goes like there are some dots that are darker than others, but he says it starts fading in and out. And all of his friends in the video, which if you ever want to see it, they start freaking out. They're like, "That's not how colors work. Colors don't fade in and out. Like, how do you get colors to fade in and out?" It's like, well, his eyes probably don't have enough of the chemical in the background or in the back of his eye to trigger for those colors. So he gets just little sporadic motions. And that's kind of the whole thing, is that color is a bit of a subjective thing. Now, one of the answers to this in the beginning, Gustavo he put FF0000. That's actually, well, this is actually a computer code for a color. Now, each of these two numbers represents a color. They represent a primary color. So let's try and list out the primary colors. See if anyone can figure it out. I'm going to draw. There's actually usually people know about two sets. So let's see if we can figure out both sets of primary colors. That's not even close to a straight line. Wow, I'm kind of sad about that. I'm going to cheat. Okay, so we got blue, yellow, red. So blue, yellow, red. All right, anybody else know any other primary colors? Gustavo, you should be able to figure the rest out, because if you know what FF0000 is red, then this one should represent what color? Or did he just look it up online and not know what it means? That is red. Yeah, so there's going to be a red. Anybody guess what the next two would be? Let's make sure my chat keeps pausing on me. Oh, I saw someone's go away. Green? Oh, RGB. There we go. Yeah. So RGB is the other famous one. RGB. This is the light primary colors. You guys remember how I used to have your stations? Didn't really state them a lot, but everyone, like in the beginning, I kind of tried to do it, but with the way the new system worked, didn't quite go. But red, green, and blue. This is red light, this is green light, this is blue light. If you combine red and green, you get yellow. If you combine green and blue, you get kind of a purpley color. And with this, you can get all the colors in the world. Red, green, blue gives you all the colors in the world. The other famous one, it's usually not in this order. Usually you see red, yellow, and then blue or something like this. This is what you might see, and people refer to it as the pigment, like when you do art with paint. The thing is, though, this is not the actual primary colors of pigment. I know people like there's a whole thing on this where people get argument over it, but the actual primary colors are magenta, yellow, and cyan. In fact, I know that like there's no audio for it, which is going to make me a little sad. But this person actually, he's an artist, Draw Jazza. He does a lot of great stuff. And he hears about it all the time where people are like, oh no, there's a, what are you talking about? It's red. It's always been the same. So he goes, here's the primary colors, red, yellow, blue. And he's going to actually go through it. I'm going to skip a little ahead since you can't actually hear it, but he's going to try and paint with them. And if you can paint with them, you'll get all the primary colors. So he's got yellow. And then he's also going to put the red and the blue next to each other so he can kind of overlay them. And over here, he's going to put the cyan and the magenta. So he mixed those two to make blue, and he's like, it kind of look more purple, but it's all right. And then he made green. He's a little shocked. Yeah. And he tries a bunch of stuff. He tries paint, he tries pencils and such. And eventually he comes to the realization that you can't make it with red, yellow, and blue. It's actually, those aren't primary colors. Yellow's a primary color, but not red and blue in the pigment form. And so he has a little bit of a breakdown. He's very sad. And he has to admit it. And it's kind of a funny thing that happens because, oh, you've seen Draw Jazza? Yeah, it's a great video. I love showing it during this lesson. But yeah, it's one of those things that we're told some stuff when we're kids and we get it kind of mixed up. But that all has to do, all of those colors has to do with how your eyeballs work, how information goes into them and actually gets interpreted in the back of the eye. Now, we're going to work our way through the eyeball a little bit today. So we're going to, color is kind of the last part, but I love opening with that because it gives you a better sense of what's going on. So first of all, for the eyeball, so let's get a little bit of an eyeball drawing here. My eyeball is drawn a little weird because I'm not an artist, but we have our cornea here, and we have our pupil, which is an opening. Now, when light comes out, let's say I have a tree. There's my art skill. The light from the tree is going to go into our eye and into the back. Now what happens is the top of the light actually goes in through the bottom of the hole. You know what? I'm going to cheat and make straight lines because I can make those dotted as well. It goes in through the hole and into the lens. And the bottom of the tree goes in through the hole and at the top of the lens. Now the lens, if you guys did the homework, you know that it bends light. It bends the light and causes the image. This one actually, it causes it to go straight and then it causes it to focus again. And if it does it correctly, no, actually, let me redraw that. If it draws it into a single point, we get this nice, clear image right here on the back of our eye. Pinpoint accuracy. If, actually, sorry, that's where the focal point is. That's if you have one of the near side. If we have it done correctly, let me get my pen back out, we will have a tree that's upside down. And that's going to project on the back of our eye. Now, how this goes into the eye to here, we're going to work through in stages. So first of all, the light that's coming out from our sun is going to travel down to whatever object. It's going to hit that object. It's going to reflect off that object. Even if it's not a mirror, it still bounces off it. Then that reflected light is going to go into our eye. The bending of the lens, I'm going to go through a quick lesson in case some people still haven't gotten through the Brain Genie or understood it. But it's just going to be kind of a quick PowerPoint that shows you how the lens works. I'm not going to spend a lot of time on this one, just kind of quickly going through it because you should have the other video, which has a really good explanation. But basically, lenses are just anything that are clear and can cause an image to, or cause light rays to converge or diverge. That means you have one of those in your eyeball. That lens inside of your skull actually bends light. It's not made of glass. It's made of protein. It's actually made of the same protein you see in chicken egg stuff. It's like, have you ever seen a chicken egg? When you crack it and you put it in the pan, when you heat it, it turns white, but we call it the egg white, but before it's heated, it's clear. Same thing with the lens in your eye. That is actually, it's kind of squishy because your eyes can focus on things far away and close to you. If you ever want to feel the muscles of your eyeball moving, here's the trick. Take your hand. It's usually easy to do this with like one eye closed, and put your hand like kind of close to your face. As close, don't blind yourself. Don't like, I can't see anything, but like, get close and try and like focus on your hand. Get it as close as it is that you can focus. It might be a little different for every person. Like try and make out like all the details on your hand, but really focus on it for a few seconds. Then after you've got a good, like pretty clear image of your hand in your face, as close as you can get it, pull your hand away and try and look away something far. You'll feel the muscles in your head as your lens gets squished and stretched to focus on things further away. That is a lens in your eye that you use all the time. Every time you've ever had to focus on something close, not only do you move your eyes a little bit inward, but you actually distort the lens in your eye. And you're doing it with muscles inside your eyeballs, completely unaware that you're doing it. But if you pay enough attention when you're going from something close to something far away, you can kind of feel the muscles move. So those lenses are really important on how we can focus light. We have what are called converging lenses in our eye. Converging lenses means that it focuses things to a single point. The light converges. If we had a diverging lens, that would cause the light to spread out and we would get no image. Now, these converging lenses are the ones that are fat in the middle and thin on the sides. They produce actual images. This is a converging lens. If you want to find out how it all lines up, we have 3 different rays. First ray is called the parallel ray. The second one's the central ray, and the last one's the focal ray. I'm not requiring you to be able to draw them. I would normally do this during class, but it's a little hard for the distance learning. But I just kind of want to show you how the whole lens thing works. So here's an object standing away from my lens. The top line of the lens goes straight parallel right into the lens of our eyeball. Then the lens moves, I just wonder if your mouse can see, the light is going to get bent through the focal point and it will continue on. Next, the light from the top is going to go straight through the center of the lens and intersect at a certain point. As long as that's where all 3 intersections occur, that is where we'll have our image. So we'll see if the third one intersects. The third one intersects by going through the focal point on front of the lens and then straight back. Now, depending upon the thickness of this lens and distortion, a lot of these numbers can change. But right here is where all 3 points meet up from this one point. So all I'm looking at is just that very, very tippy top of the arrow. And that means right there is where the tippy top of the arrow is going to be down, upside down. If I did this for every single point along this arrow, I would get every single point of the arrow along here. Since we're doing just simple versions, you can just draw an arrow and make a near mirror image. But that's how our eyes work. It pulls all of the little dots from every single object and it goes through our lenses and they all bend at different spots and they all hit the back of the eye where it triggers a different chemical reaction based upon color and intensity. So there's a bunch of different converging lenses that can occur and stuff we're not going into. We can even see stuff from extremely far away by going into our focal point. But like I said, I'm not going into too much of that. I wanted to kind of end. Yeah, I'm not going to go into the diverging lens and the converging lens, but I am going to do a much better job of drawing that eyeball. But I want to take a second. Are there any questions? I want to make sure I haven't missed any chat. Why is pointing a laser? Oh, okay, we'll cover both of those. The eye is open. You want to have your eye open when you're doing this. So when you're trying to look at your hand close, if that's where the question was, you want to like, you could do it with both eyes if you really want to. It's just, it's hard for you to see that on camera. But as for why is pointing a laser at you bad? Well, let me just kind of give you a visual. People think, oh, well, so what if I point a laser at my head? The sun's out. It's way brighter than the laser, right? And that's going to be much, much brighter. And it's true, if you stare at the sun, that's bad. But the sun is really, 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 really far away. And if you remember some of our talk from like vectors and projectile motion and such, if I have a flat line and then I have another line that isn't quite as flat, just a little bit off, just a little bit off, you can see that as I get further away from the source, it gets spread out more. Same thing with the sun, the light from the sun. It is far less intense than it is closer to the sun. You're going to get less of it. It's getting spread out over a much larger area. Kind of like if you get a piece of a nice glob of like peanut butter on a sandwich or mayo or whatever. You probably don't like mayo. A lot of people don't. But like, yes, you can go blind. So like, let's say you want to put some peanut butter on some toast, and you got a big old scoop of it out. Well, a big scoop, you're like, oh, that's a lot of peanut butter. But then you start spreading it over just one piece of toast, and maybe you have just enough for that perfect piece of toast. You're like, oh, that's great. But then someone goes, no. You need to share with many more people. You have to spread that peanut butter out thinner and thinner until eventually there's just not enough peanut butter on any of the slices. And that's what happens as you get further away from the sun. The sun's light gets spread out thinner and thinner and thinner. It's still bright and will still hurt you. But the amount of energy that is hitting from the sun on one area, so like let's say the sun's ray of light's coming out, it hits an area like this, is a certain number. So I don't remember what the number is off the top of my head. It's like 1,000 kilojoules of light per hour or something like that. That is amount of energy per area. Your eyeball is a tiny area. I mean, look at that. If we talk about with the amount of sun the area is hitting, it's over a large area. Your eyeball is very tiny. So you're only going to get a fraction of that number, right? Just a small fraction. However, a laser, it doesn't spread. A laser focuses all of the energy inside it into a single beam. And it does spread like very, very, very little bits, but not that much. So the amount of energy being pumped into your eye is sometimes on the order of hundreds to thousands of times of you staring at the sun. Because even though the sun is super bright, it's so far away and all of the energy has time to spread out, you're really getting a fraction of a fraction of a fraction of the area, because your eye is small, that you're actually getting into your eye. It'll still damage you, but it'll take a little longer. A laser going into your eye, especially those pocket lasers, or if you get a higher level one, like a kilojoule one, you're getting all of that kilojoule, 100% of it, straight into your eye. And it's kind of like when we talked about with radiation. The danger isn't you being exposed to stuff that's kind of far away. It's when it gets inside you, and especially if you have a large concentration of it inside you. A laser fires a large concentration of it straight inside you. So I hope that kind of clarifies that. Let's get the chat reset. You want a sandwich now? Okay, well, I'll try and go through this semi-quickly. But you know what? I'm just going to, I have a human eye. Let's just steal one of these eyes. What's a good one? That's a pretty good one. It's not theft, it's for education. All right, shrink it down a little bit. Okay, so we got our eyeball. Now, make sure you guys can still see me. Any questions? Oh, it's cornea. But yeah, I get it. Not what I want. Okay, so your cornea and your pupil and all this part, that's the bump on your eye. So like if you very gently put your fingers over your eyes when they're closed, everyone, and you move your eye, like you look left, you look right, you look up and look down, you'll feel a little bump moving around. That's the cornea. It's part of the eye that extends out over the pupil. So the pupil is actually, well, it's a hole. Now the lens is usually back here a little more in diagrams, but this is actually a little more accurate. It's not too far back behind your pupil, your pupil. All the rest of this of your eye is, oh, you shot, don't, what? Why? I know I don't want to know. Do I want to know? Why'd you shoot the bump? Okay, that scares me. But this lens redirects the light that's coming in. Now, just like before, we have some sort of object. So let's draw our horizontal line here. And I have some sort of object like an arrow. I'll make it a little shorter because the lens in this one's drawn a little shorter. And we can see, let's make this different color so it's easier to see. In fact, we can do this all with straight lines too. So that first line goes through here, hits the lens, and then it's going to extend out through wherever the focal length is. Now, depending upon the lens, it can change its focal length. You witnessed changing its focal length. When you focus on something close and you focus on something far, you're changing your focal length. Your eye is determining where it's going to start focusing the image. In fact, if you can kind of trick your eye, if you can focus on something close, you'll notice that all the stuff in the far distance gets blurry. And when you look at something really far away and you put something close up to your eye, like your hand, it's kind of blurry and faded. It's because you're actually using two eyes. But it's going to send the light through wherever, and then this one's going to go through wherever that focal length, through the center. It's going to meet up somewhere. And then this one's going to go through wherever that focal length is to the lens, and then send it out. Now, all three of these are going to project. If you try and focus on something really, really close, you're going to strain the muscle really hard. That's why I said don't be like, look, I can see, it's a muscle. It's going to exercise. So it's actually a good thing to work out. If you've been staring at a screen for a long time, you've been using a lot of close range muscle focus. So you want to, every once in a while, I think it's like every 20 minutes to a half hour, look away from a computer screen and focus on something far away to get your muscle to move towards the other side, other direction of your vision. And there are glasses that can also help with that. And that actually this is where glasses come in. The version I drew right here, if you notice, this arrow is not on the back of the eye. The part of the eye that you actually see with is all along the back here. All along the back here, there's all these chemicals. And I don't remember the exact chemical diagram, but it looks something like this from my memory. And it's really kind of interesting is that there's like this weird little hang-off part. And there's an open spot here, but there's a hang-off part here. And what happens is the light comes in, and there's like a little triangle hole here. It hits this part. I'm going to try and use a different color to make this easier to see. It hits like this part right here that holds this together, and it causes this to snap shut. And it's saying red, 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 red. The more of these chemicals that go, it's kind of like an applause. If there's just one person clapping red, you can't really hear it. And there's like a little spot of red in your vision. But if you have an entire auditorium, it's going to be much more red. Same thing with the green. Same thing with the blue. If you have more than one of those colors going, and at the same area, then you'll have more than one of those colors appearing and it'll start overlapping. That's actually how we get all of our other colors, such as yellow, which is green and red. If you've ever seen purple, that's actually blue. And here's the funny part: pink doesn't exist as a color. It doesn't actually exist as a wavelength. There's no pink wavelength. All the other ones, red is about 330 nanometers. Sorry, that's blue. Red is about 720 nanometers. Green is 550. Blue is around 330. There's no pink. Pink is actually because our eyes take the red and they take the blue, which are on opposite ends of the spectrum, and stick them together and make a color that doesn't actually exist in nature. Weird, isn't it? Ooh, still drawing. I don't know why. Okay, what's going on? Oh dear. Did my computer freeze? All right, let's see if I still got you. Okay. Let's see if okay, just want to make sure because I'm afraid of this thing like cutting out and you won't hear anything. Okay, now so through this version, the object is not on the back of the eye. It's not clear. In order for us to be able to see it, this needs to be projected right here on the back of the eye, which means that all of these arrows would need to line up here. This person has a vision problem. And I'm actually going to be honest, I already looked this up, but I've already forgotten. Nearsighted, farsighted, the exact where the image appears. So I'm going to double check it. Like I just completely in like the time between I was here, I forgot it. Okay, so as you can see in this one, this is a great picture. I should have just taken this one. I just need the picture. Fine. So normal vision, you can see that the image would appear cleanly on the back. It perfectly lines up. Nearsighted people, the image appears too far in front. It needs to go further back so that these arrows come in at a much shallower angle, which means that it would create the image further on the back of the eye. People who are farsighted, they can't see the stuff that's close up. The lens focuses the light behind the eye. And people who have other problems such as astigmatism, where basically the lens isn't smooth, it's got problems with it, so it focuses different parts at different distances. So if you're a person who wears glasses and can't see things that are close to you, but you can see stuff that's really far away, that's farsighted. It means you can see things that are far away. If you are nearsighted, then you are like my dad. He was very nearsighted. And if he ever wanted to look at a watch, like let's say this was his watch, first thing in the morning, before he put glasses on, he would have to take his watch and look at it like this. He had to bring it up that close to his eye for him to be able to read it. He had to get actually laser eye surgery because his vision was that bad. He now wears a very thin pair of glasses because he got it back in the 90s and it's been 20 years and eyes still degrade. But yeah, so anyone wears glasses, they are probably one of the two most common, which is nearsighted or farsighted, though astigmatism does happen as well. And that's why we take you for the testing every once in a while to see which one you are. What happens is that so this version is nearsighted. If I put another lens in here, in front of the eye like this, right here, I can change where all of these arrows adjust to. I can make it so that it will bend out a bit more. This one won't go as, come on, grab it, go as straight, and it will cause this one to bend a little bit differently, and it will cause the image to appear at a different spot. That's what a lens does. It redirects light. It bends light. So your eyeball, which is a fantastic, amazing contraption, is really just a squishy ball that is full of seawater. That's what's inside there. It's effectively seawater. It's salt water. And it has the equivalent of an egg white acting as a lens. And yet through it, we see all things. It's how we experience most of the world. There are people who don't need it necessarily, Sora. Farsightedness just means that it's easier to focus on things far away. It's if yours is only just slightly, I'll get to that in a second, Daniel. But there's a range. Basically, if you have, like, if your vision, let's say you have farsighted over here, and near over here, and what they call normal over here. There's like a spectrum. If you're like anywhere within here, you don't need glasses. If you're over here, you really need glasses. So you might be like here. You're technically farsighted a little bit, but you don't need them. You can get through life just fine. It's just, you know, when you're trying to read, and my friend used to do this, it was kind of funny. We always make fun of him for it. Some people would be reading something like this thing would be reading it right here. But other people who have just slightly farsightedness would have to pull a little further back. And every once in a while, you'll see people do this kind of stuff as they're looking at it like, you know, that kind of look. That's people who have a really farsighted vision probably should have glasses. As for why tears are salty, that's a whole different thing, because tears happen outside of the eye. Your eye is not leaking. Like, it's not like you punctured a hole in it. The tear ducts are actually down around here, and they're pushing out water and saline and a few other chemicals out of your system. You can actually look at tears underneath microscopes and look at the crystalline structure of the different chemicals. Different tears come out for different reasons. If it's sadness, it looks different than if it's stress, because you can actually start crying just because your body's stressed. You're not sad, but your body's just so overloaded, it's so overwhelmed that it's just like, I gotta get this stress out of me. I gotta get the stress hormone out of me, and crying can actually get that out of you. So like, crying doesn't just mean you're sad. It can mean pain, it can mean sadness, and it can be stress. And there are actually different chemicals in the tears when those happen. So I don't know if they're more salty. I'm not 100% sure about that. I just know that the structure of the crystalline chemicals, like salt to crystalline chemical, differ. So I don't know if they're more salty. But crying happens because your body's trying to do something. Either in order for your body to trigger release of anti-stress hormones to alert others around you that you are in danger and need of help for social structure, to convey sadness or an apologetic structure to let people know that you feel that something wrong had happened, or to even just like help balance stuff out. I mean, I remember as a kid once when I was really sick as a kid, I had to take a lot of medication. One of them messed with my whole body chemistry, and I was sitting in class and my teacher was like, "What's wrong with you? Are you okay?" And I went, "Why? What?" And apparently I had been crying. Tears had been streaming down my face. I didn't even know, because it was just my body was so overwhelmed from all of the antibiotics that it freaked out and started crying. I didn't have any control over it. I wasn't sad. I wasn't hurt, but my body was just so overworked that it had a breakdown and it couldn't handle it anymore. So I don't know if they're more salty, but yeah. Can absolutely be from happiness. That's the overwhelming. That's the it's basically when your body gets overwhelmed. There's too much emotion, too much stuff happening, and your body goes, "I can't take it anymore," and just like goes cry. So that's basically how that kind of works. So the eyeball is a really neat thing. And I wanted to show you some of the other videos, and I suggest that you look it up. Here's a great one. They used to be up on Verve, VRV. I don't see it up there anymore, but it's I'll put it in the link just so that it's up there and recorded. If you Google search that, you can find it on like Daily Video or something. It's a really great structure on how the eye works. And in fact, I'm going to skip to one part. That's actually an old Irish legend, which, as an Irish person, I find quite nice. But I want to show you some of the things that people thought on how vision worked. So in the past, people thought that they could see because they shot fire out their eyes. Think Cyclops from X-Men. So like he thought that you shot fire out of your eyes, it hit the stuff and then came back. And that's why you could see things. So it like literally traveled into you. And he didn't really explain why, and a lot of people had questions about it, but they didn't have a better answer. And part of the reason why is because if you ever look like a cat at night, you can see that like inner fire. Not everyone accepted it. They weren't like, obviously, this is exactly how it works. People were like, but that doesn't explain everything. And they're like, you got a better answer? No, but then we're sticking with this one. And that's kind of how science works. You come up with an answer, you test it, and you keep the best one. And then you wait till someone comes up with a better one. And eventually, they were able to figure out some more information on how the eye actually works. And it's not through visual fire, because a person, let me get to him. This guy literally cut up eyeballs. Now, this is the story, and I'll leave you to watch it if you want, but this is the story basically of how the eye, he was so blinded by the previous thought that he's like, this must be how it works, that when he found the crystalline humor that's actually the lens, he thought that this thing going off the back was where the fire came from. But that's actually your optic nerve. It's actually how the signals from your eye go into your brain. Now, it wasn't until much later that a scientist came along where when people asked him and like, well, how does it work? He goes, I don't know. I don't know biology. I just know this is how an eye works. I'm not going to lie and pretend it. But he created the first camera. In fact, this is a camera. A camera is actually just defined as a dark chamber. So what he did is he put a little hole in the wall, and when the light was coming in from the outside, it would project through the small hole and onto the other side, and you get an image of the outside. In fact, recently there's been a lot of Reddit and a couple of trending images around of people taking pictures of their bedroom first thing in the morning, and you can see a projection of the outside world on their wall. You can actually do this in any room if you take if you block out like most of the light, and you get a nice dark room, and you put a small hole like in a piece of paper, or like if you got like cardboard or aluminum foil. Do it in a room where you already have like only like one window of light coming in. Don't do like the room that has like 17 windows or 6 windows or something like that. Make it easier on yourself. Or if you want to do this, you can also just get a box, get a nice dark, kind of semi-decently sized box, puncture one little hole in it, and then on the other side get like have a place for you to look at on the top, and then put a towel over it so that no light gets in, and you'll be able to see, if the room's bright enough, an image from far away. It works really well if you can do it outside a window. I would show you, but distance learning and such. But in this one, he actually watched like an eclipse. In fact, if you go to my website, there's a video of the eclipse that happened a few years ago that I filmed on the roof of our school, and I did it through this. I used a telescope as basically a projector for a camera structure, and then filmed the camera projection. But he noticed that everything was upside down. And the reason why is the light comes from the top, goes through. Yeah, and that's how the eye works. And it's a great video, and I suggest that you watch it. But make sure there aren't any questions during that time. Your room doesn't have anyone, well, like I said, then grab like a box, you know, any size box that you can get a hold of. Like I have one here. Now you'll have to tape up all of it so that you can't see anything inside it. If you don't have one this size, you know, you could even do it technically with a cereal box, but you want to have it long ways. But you want to try and make it so there's a little tiny hole in it, like a pinprick. Like take like a safety pin or a thumbtack or something like that, and put a small hole on one side. Then on the other side, about 90 degrees, you're going to want to have a way to look in. So you cut a little hole for your eyes, but you got to make sure that you can cover it. So you want to get like a towel or something to block all the light. And you'll see that on the other side, opposite of where you puncture the hole, there's an image. It's actually upside down. It works really great if you do it like say outside, because then you get a lot of bright light and you can actually like make images out of like bushes and trees and things like that. And what you effectively made was an eyeball. I mean, it didn't have a lens, but you made an eyeball, because that's what a camera is too. A camera is nothing more than a dark chambered room. That's what the word camera originally meant. And your eyeball is nothing but a dark chambered room. It's a camera. It's an organic camera. It's just instead of producing film, what we have on the back of a camera, which is a type of chemically treated material that when exposed to light, it etches and creates color and such. Ours takes that light and it hits a different kind of chemically coated background, but instead of etching into it, it sends a signal up to our brain that then registers the color. So I know I kind of went really short over the whole lens part, but I figured the first video kind of helps with that. Are there other questions about the lens? We have been doing this for 50 minutes, so I don't want to like take the rest of your time unless you have specific questions, because I could talk about this for like a long time. Fact. Like if you want to learn more about like the vision one, or like about the vision, it's a group called Achievement Hunter testing colorblind glasses. It was a great one because you can hear people like responding to him saying, yeah, it kind of fades in and out. They're like, how, that's not how vision works. What is your world like? To the RBG color, which afterwards makes a very nice drawing of two superheroes, to the actual structure on how your eye works. I suggest watching all of these. They're great videos for stuff. Okay, I have a question, but not on this. All right, Rachel, sure. I don't mind answering those questions, but I do want to make sure I get, before I answer that question, I want to make sure, are there any questions on how to calculate the lenses for the Brain Genie, which is due Friday, or anything like that? Because if it's not on lenses, I'm probably going to stop the recording and answer questions individually if you have them. Like that's fine. Like if you have any other questions, great time to ask. Yeah, I'll do that. I have no problem. Actually, it might be not a bad idea to do the science fair questions in the recording. So is your question about the science fair too? Okay. So I'll do a quick version of the science fair breakdown, and then I'm going to stop the recording, and then I'll answer any individual questions we have about any topic. So science fair breakdown. Next week, Wednesday, 1 week from when I record this, your paper is due. It's, depending upon which period you have me for, it's either 2 to 3 or 3 to 4 pages long. There needs to be a diagram. A diagram is a drawing that shows me what your object looks like. Does it have to be a perfectly blueprinted diagram? No. If you want to, there are videos on my website and my YouTube channel that show you how to blueprint an object. but I'm not requiring it. I just kind of need to know what it sort of looks like so that when I'm reading through it, I have a visual example. Think back to when you made your egg drop. In there, it said you had to draw a picture of the inside and outside of the device in order for us to understand what it looked like, and what the materials were. I'm basically asking just for that. You're going to start with your intro. Tell me what is your problem and why is it bad? Write a page on it. Yes, it's double spaced, so you got a lot of extra things to work with. After the introduction, you're going to then want to introduce me to your actual problem, which is your method, your middle section. You introduce me to the device, you tell me how it works, how it's going to fix everything, and what backup you have that says, yeah, this kind of thing should work. Kind of like when I gave the example in class about the vacuum cleaner. Vacuum cleaner may never have existed, but an air pump had existed, and saying, hey, when air pumps are used, it causes things to move. We can blow and suck things. So we're making something that sucks things. A beater brush didn't quite exist, but beaters did, where you beat the rugs. So it's just saying, hey, it's one of those spinning around in a circle. We know the beater works. This is just a beater spinning around in a circle. So it's using previous existing information and technology to prove that this one should work. That's the important thing. It doesn't have to actually work. You don't need to build it. You don't need to actually make a model. You just need to give me enough evidence to say, hey, if we were to build this, things tell us it should work. Not just that seems like something that works. No, it's like, I've got some other people who have done work that are similar to this, and we know that this works because of this science. That's all I'm asking for. Conclusion, what are the changes to the world when you actually build it? Like, how is this going to affect things? What is the outcome? What are some future plans? The paper I'm being very light on the grading this time because of the whole distance learning. I know it's hard to get in contact with some of your fellow members. And after I get the papers in Wednesday midnight, on Thursday, I'm going to send out the sign-up sheet. All right, now I'm going to try and look at the chat, see if there's any other new questions. Okay, I'm going to stop the recording if there's no other questions on lenses. That way this can get uploaded. And then anyone who has questions on anything else, just stick around and I'll answer them. So let me hit the stop button.